Hello, this is Jerry Tuttle, and I'm here to discuss the mathematics of love, or love is irrational. I'm sure we all know that math is being used nowadays in more places than ever, so I think a natural question is, what can mathematics tell us about love? So first, if you think about it, math and love are pretty similar. In math, we have a problem, we try to understand the problem, identify potential techniques to solve the problem, choose the best technique, and implement and check the answer. In love, I think we all understand the problem. We're looking for love. What we're identifying, though, is potential partners. We want to choose the best partner and then implement, although I'm not sure about how to check the solution. Before I get too far, please excuse the blatant sexism of this talk, but I will only be talking about the case of boy seeks girl. There are 4 or more permutations to the boy seeks girl. These other permutations are certainly equally valid. The math is no different, but for simplicity, I'm only going to discuss boy seeks girl. So first, let's identify potential partners with the golden ratio phi. There are many ways to construct a golden ratio, which has been known to the ancient Greeks, among others, Pythagoras and Euclid. If you have a finite line segment, there's probably some place on that line segment. If you pick the right place, you can divide it into 2 smaller segments A and B, such that the ratio of the whole line segment A plus B to the longer segment A equals the ratio of the longer to the smaller b. And for that ratio, mathematicians have assigned this ratio the Greek letter phi. You can manipulate these 2 ratios into a quadratic formula. The positive solution to the quadratic formula is 1 plus the square root of 5 over 2. It's an irrational number. Rounded to 3 places is 1.618, and that's the rounded value of phi. And phi is said to be an aesthetically pleasing number. Phi has been used widely in art and architecture. Renaissance artists certainly knew about it. Much architecture can be shown to have various golden ratios within it. This is Da Vinci's Salvator Mundi. A more recent proponent of the golden ratio in art is Salvador Dali. If you ever visit his museum in St. Petersburg, the docents are more than happy to tell you about Dali's use of the golden ratio. But let's get to love. So I had asked a cartoonist to draw me a picture of an attractive woman. And here's what my cartoonist came up with. We've named this woman Jade. I didn't ask my cartoonist to do anything specific other than give me an attractive woman. So the question is, how would you rate her? Would you rate her on a scale of 1 to 10, an 8 or a 9, a 6 or a 7? How can you be sure? Well, of course, what else would math people do to answer that question? But we'd measure her. And I've done that. So I've measured the length of her face, the width of her face, her interocular distance, which is between the inner corners of the 2 eyes. I've measured the width of her nose, the width of her mouth, also the distance lips to chin, and the ear length. And what are we going to do with those? We're going to see if various combinations of these measurements in ratio form exhibit golden ratios. And here are the 6 I've chosen. I've chosen these because scholars have studied various ratios, and there are at least 20 facial ratios that people have measured. Scholars have decided these 6 correlate the best with opinions of beauty. Face length to width, mouth width to distance between the eyes, and so on. So I've measured Jade for these 6 of these. Actually, this is the closest one, ear length to nose width. The others are pretty far. If you take the arithmetic average of these, you get 1.289, which is not all that close to phi. And if beauty is in the phi of the beholder, jade is not especially attractive. But what about other people that we might agree are more attractive? So I've measured a number of celebrities. Scarlett Johansson and Taylor Swift I would consider very attractive. Their percent deviation from phi, averaging the 6 ratios, is under 3%. Lupita, I don't know how I pronounce that, is a very attractive black woman. She's at negative 3.3. I consider Ryan Gosling and Brad Pitt attractive men. They're in the 3s. I'm at negative 9.7. Not a surprise, I'm pretty far from phi. And interestingly, the Mattel doll Barbie is right at phi at negative 0.3. So Barbie, who has been known to have unrealistic measurements below the neck, perhaps has unrealistic measurements above the face too. Then I've also measured a number of non-celebrities. I measured 20 non-celebrities, and I measured their average deviations from phi. And then I asked one of my classes to rate each of these non-celebrities on a 1 to 10 scale. For each of these non-celebrities, I averaged the ratings. I averaged their percent deviations from phi. I plotted them, found the linear regression line, the R-squared value, which is kind of low. And obviously there's quite a bit of variation here. It's certainly generally true that the people with the higher ratings from 1 to 10 are generally the people with the lower percent deviations from phi, and vice versa, although there are people in the middle, and this line doesn't fit real well, but certainly it seems to be generally true that people whose facial measurements have a small deviation from phi are getting favorable ratings on a 1 to 10 scale as well. Plastic surgeons turn out to know about the golden ratio in facial attractiveness, but to my surprise, so do makeup artists. And there's a Beverly Hills makeup artist, Anastasia, who's patented eyebrow stencils. And her eyebrow stencils explicitly use golden ratios in their patent and presumably in their stencils. So let's see how Jade does with her eyebrows. So once again, I measured Jade. This is the same Jade as before. I'm measuring now her eyebrow length, and then I'm starting from the very top of her arch and dropping a perpendicular line down to see where it intersects the horizontal. And this now takes the horizontal line and splits it into a longer line and a shorter line. And if we take the shorter line and call that starting point to high point, and if we take the, I hope I said the longer line, if we then take the shorter line of high point to end point, Jade's ratio is 1.621, which is quite close to phi. So Jade has very good phi brows. Also near perfect phi brows is Juliana Margulies, the actress in The Good Wife. I always thought she had good eyebrows. So that's how to choose an attractive partner. Now, how do you choose the best partner? Barbara Bush's solution was, I married the first man I ever kissed. There's certainly something sweet about that, but the question is that really optimal? So suppose this is me, and I'm at a singles bar, and I'm interested in choosing the best of a set of attractive single women. There's a large number of attractive single women. I want to maximize my chance of walking out the door with the best woman, whoever I decide best, But we've now taken attractiveness out of this because these are all attractive women. So I need to chat with a woman to determine my preference. I'm going to chat in random order, one at a time. And after chatting with a woman, I need to make a decision. If I decide yes, she accepts. Obviously, this is a theoretical mathematical model, not how it's done in the real world. But if I say yes and she accepts, then I'm done. If I say no, then I've lost my chance with her. She's gone forever because I'm not the only guy in that bar, and I have to chat with the next woman, but she's gone forever. So what is the optimal strategy to maximize the chance of walking out the door with the best woman? So the optimal strategy is called look, then leap. Now, if you select the first person, your chance of getting the best person is 1/n. You'll get the best person 1/n of the time. Similarly, if you select the last person, you get the best person 1/n of the time. So certainly you want to do better than that. It turns out the optimal strategy is look, then leap. So look at the first R-1 women and you use the first R-1 to collect data. Having collected data on these R-1, then leap at the next applicant who is better than everyone you have seen so far. But how do you decide on the value of R-1? Well, if you think about it, and this wasn't obvious to me, but I played with this for a small value of the n applicants, you'll see the probability of selecting the best applicant for any value of r is going to be 1 over j minus 1, where the j's go from r to n. So these are the remaining people left in the population. These are summed and they're all multiplied by r-1 over n. As I say, this is not obvious, but if you play with it for, say, n equals 5, you'll see it makes sense. And it turns out the optimal r that maximizes this function is r over n equals 1 over e, and that's our old friend e, the natural logarithm base, and 1 over e is approximately equal to 37%. So let's see how this works for a small number of cases. Let's do n equals 5. For n equals 5, 37% of 5 is 2, rounded, so we should look at 2 people and then leap. So suppose my preference is 1 is the best, then 2, then 3, then 4, then 5. There are 120 cases to look at. Case 1, suppose I interview number 3 first, then number 4, then number 2. Number 2 is now my third applicant. I would leap at number 2 because number 2 is better than either 3 or 4, but 2 really wasn't the best. Here's another case. Suppose I interview 5 first, then 1. The third applicant is 2, but 2 is not better than everyone else. The next applicant is 3, which is also not better than everyone else. Finally, I have applicant number 4. I have to leap at number 4, but that's not the best. If I test all 5 factorial permutations, this strategy will select the best 43% of the time. And in fact, for various values of n, here is the r-1 value to start leaping at, and here are the probabilities. And as n gets large enough, we converge to 1 over e. This strategy also works with applicants over a lifetime. If your dating life expectancy from age 18 to 14 is uniform, this says collect data through age 25, and at age 26 it's the time to leap. This is in the literature as the secretary problem. It also applies to looking for a parking space, apartment, selling a house, and so on. It's widely discussed in the literature. So we've used irrational numbers phi and e. We could also use pi in coming up with a cardioid. Love is irrational. Did I use this method personally? Well, I guess I didn't. This is my significant other. I did not use the 37% rule with her. Here are the references I've used. I hope you've enjoyed this talk. I enjoyed researching this topic, and I thank you for listening.